Hi students, today we're going to do a little bit of review on periodic trends. We've already talked about most of these, and there are a couple of others that we're going to add in as well. So we're going to go through the PowerPoint that you've already seen and just catch a couple extra things here that we didn't talk about yet. So we talked about Dmitry Mendeleev developing the first periodic table, and we talked about the fact that there are lots of trends on the periodic table that he used to develop that. And it has a lot to do with where electrons are located. So we said that electrons can be located in orbitals around the nucleus, and the first energy level around the nucleus has 2 electrons that it can hold and no more. Energy level 2 can hold up to 8 electrons, and energy level 3 can hold up to 8 electrons as well. But that's only sort of true. If you did the electron configurations activity on Tuesday during the e-learning 7-period day, you probably noticed that energy level 4 gets 2 s electrons filled first before the 3d electrons get filled in there. And so that's why your outermost energy level, the maximum number of electrons you could have there, because now we'd be bumping up to an energy level 4 next. The maximum number of electrons you can have is 8. So 8 is the maximum number of electrons you can have on the outside of an atom, and that outside is called the valence shell. So valence electrons are important because they determine bonding behavior of an atom. They're the ones in the outermost energy level. And the trend for valence electrons looks like this. Everything in this column has 1 valence electron. Everything in this column has 2, this column has 3, 4, 5, 6, 7, and 8, with the exception here of helium, which only has 2 electrons. They're valence electrons because they're in energy level 1. Energy level 1 can only hold 2 valence electrons, or 2 electrons. And so helium is grouped with the noble gases because it behaves like one, because it has the number of valence electrons, the maximum number that it could hold in that outer energy level. And then these guys, the D and F block elements, have 2 valence electrons. That includes these guys down here. Let's see. Yeah, hopefully you can see that arrow. So let's look at the periodic table, grab your periodic table and check it out, and do a couple of practice problems here. Find magnesium. Magnesium is over here. How many valence electrons does it have? Pause right now. The answer is 2. Next, find technetium. Technetium is down here. Pause the video. Find it. See how many valence electrons you think it has. And the answer again is 2. Now find aluminum. Aluminum is here. Pause the video. Aluminum has 3 valence electrons. And let's find silicon right next to it. Silicon has 4 valence electrons. Sulfur is over here. Sulfur has 6 valence electrons. And bromine is down here. Bromine has 7 valence electrons. And then neon up here has 8 valence electrons. And of course, helium here only has 2. All right. You can use valence electrons to draw Lewis dot diagrams or Lewis dot structures or electron dot diagrams, or any of those names mean the same thing. You write the symbol of the element and you draw the number of dots around it that corresponds with your number of valence electrons. And we'll be doing that quite a bit in the next unit. We talked about the fact that vertical columns up and down on the periodic table are known as groups or families. They mean the same thing. Horizontal rows are called periods, and they are numbered. And for the families and groups, there's a couple different ways you can number them. You can number them 1 through 18, or you can number them 1A, 2A, and in this case, if you're using the A and B thing, it would be written on your periodic table. Either way is okay. I typically will use the 1 through 18 format because it's just a little simpler. And then going down for the period numbers, these are down on the side here. Sometimes they're written in, sometimes they're not, but it's just 1 through 7. So that's pretty easy. The only thing you need to know is that these guys, these are called the lanthanide and actinide series. And it's, whoops. So the lanthanide and actinide series right down here go with the elements lanthanum and actinium, so they're easy to remember. They actually belong right in here, in between these two elements and then these elements over here. So the lanthanides are part of period 6 and the actinides are part of period 7. And then we did some practice problems there. And okay. Then we talked about some specific families that have special names. We've got the alkali metals here, which, by the way, does not include hydrogen. We've got the alkaline earth metals next, then the halogens, and then at the far side, the noble gases. Again, the noble gases are ones that all have their outermost energy level of electrons filled. And so because of that, they never bond with anything. So they're kind of boring, but they do some cool stuff. Helium's fun. Some other sections on the periodic table have names. These two sections here are known as the transition elements or transition metals. They're all metals. These are known as the representative or main group elements. And then we need to talk a little bit today about metals and nonmetals. We've talked about it a bit, but here are where the nonmetals are located. The metals are approximately here. Most elements on the periodic table are metals. And then in between the two, and if you have a periodic table that looks like this, it's got the stair step. In between the two, we have what we call metalloids or semimetals or semiconductors. They're substances that have some characteristics of metals and some characteristics of nonmetals. We talked about which elements are diatomic. They're the one, excuse me, the ones that end in gen or ene. So that's nitrogen and oxygen. All of the halogens, fluorine, chlorine, bromine, iodine, astatine. And then hydrogen over here, hydrogen. So if you remember the gens and the enes are diatomic, then you'll get those questions right. We talked about the trend for atomic size or atomic radius. As you go down on the periodic table, the atoms get bigger. As you go to the right, in general, they get smaller. Doesn't always follow the rule going to the right exactly, but it's pretty close. So, properties of metals and nonmetals that you need to know. Metals conduct electricity well. They are malleable, which means if you hit them with a hammer, they don't shatter everywhere. They dent. They are ductile, which means you can draw them and stretch them out into a wire. They tend to lose electrons in reactions. They have low electronegativity, which we'll talk about later, and slightly negative electron affinity, which we'll talk about later. Metals tend to be found in bases, and they're shiny. So if you're asked to give me a couple properties of metals and you include the word shiny, you get credit for that. It seems kind of silly because it's so obvious, but it's true. Nonmetals, on the other hand, don't conduct electricity well. They are brittle. They tend to shatter when you hit them with a hammer. They're not ductile. You can't make wires out of them. They tend to gain electrons in reactions. They have high electronegativity, very negative electron affinity. They tend to be found in acids, and they tend to be dull rather than shiny. So trends for metals look like this. As you go to the right, atoms get less metallic. As you go up, also atoms get less metallic. So francium is the most metallic element, helium is the least metallic. So now I could ask you questions like, which of these do you think would be most able to conduct electricity? Beryllium over here or neon over here? And of course the answer would be beryllium because it's over here with the metals, farther to the left than neon. Okay, we got to talk a little bit about electrons, and I'm going to pause here for a second. Okay, so there's a new vocab word that you got to learn today, and that is isoelectronic. Isoelectronic means having the same electron configuration as something else. So for example, when fluorine atoms gain an electron, they get a -1 charge because they have one extra negative charge, and they become isoelectronic with neon. So here we have fluorine. It's got 9 electrons normally, but if it gains one, then it has 10. So it's going to have the same electrons in the same locations as neon. Do you need to be able to tell the locations? No. but you should know that it would have the same number of electrons. And it turns out that atoms tend to really like to be isoelectronic with noble gases. So they tend to gain or lose electrons, and thus they form ions, in order to be isoelectronic with the nearest noble gas. Not the previous noble gas, but the nearest one. So atoms want to have the same amount of electrons as a noble gas, because that's a full outer energy level. And having a full valence shell is something that's very comfortable for atoms. There's another thing you need to know about electrons, and that is called ionization energy. It's another periodic trend. So ionization energy is the amount of energy necessary to remove an electron from an atom. And it's very hard to get electrons to leave atoms for some atoms, but for some atoms it's really easy. And it turns out that the higher you go on the periodic table, the more up you go, and the more to the right you go, the higher the ionization energy is. So the more energy is required to pull an electron off of an atom. So it's very easy to remove an electron from an atom that's low or to the left on the periodic table. It's very hard to take an electron away from an atom up and to the right. So because these atoms are going to try to become isoelectronic with the nearest noble gas, like we talked about fluorine trying to be similar to neon, there are some trends that you'll find. So fluorine will try to gain 1 electron. Oxygen is 2 spaces away from neon, so it tries to gain 2 electrons. So when it does that, its charge will be -2. Nitrogen atoms tend to try to gain 3 electrons. Carbon atoms sometimes tend to gain 4 electrons, but sometimes they also will lose 4 electrons. So a carbon atom has 6 electrons. So if it loses 4 of those, now we're down to 2. So 2, having only 2 valence electrons, would make you similar to helium. So that actually works for that. So carbon could do either one, gain 4 or lose 4. So the general rule for charges looks like this. The alkali metals plus hydrogen, have a +1 charge when they form ions. The alkaline earth metals will have a +2 charge. We're going to skip over the transition elements because they're pretty weird. Boron's family tends to have a +3 charge. They lose 3 electrons. Carbon's whole family will have either a +4 charge or a -4 charge. And sometimes it's hard to tell which, but we'll talk about that more later on. Nitrogen's family tends to have a -3 charge. Oxygen's family will be -2. Fluorine's family, the halogens, will be -1. And the noble gases don't want to gain or lose electrons at all. They're happy with what they got because they have that full outer energy level. In the transition metals, the charge can vary, and I'm not going to ask you to predict it, but you'll have numbers somewhere between 1 and 7 most of the time. If you have the right kind of periodic table, sometimes charges are listed. You got to be careful with this because sometimes they'll give you all the possible charges rather than the most common charge. And what we're going to be asking you for on the test is definitely the most common charge for each element. You can also talk about reactivity a little bit. Reactivity is shown in the red areas. So for metals, the elements are more reactive if they're down and to the left. And for nonmetals, they're more reactive if they're up and to the right, except of course the noble gases, which are not reactive at all. Okay, so that's the notes for today, but we're going to do a review assignment now, and this assignment is a little bit different. So I wanted to show you what you need to do. First of all, you've got this periodic trends review game link that you're going to click, and it's going to give you an option to copy a document. So you're going to yes, copy the document, and it looks like this. And obviously we have here the top portion of a periodic table and some random symbols on little cards. And if you click the cards, you can drag them onto the table. Now, getting them in the right order is the main point of the game here. So we're going to go back to our daily agenda and click on this periodic table game.doc. That will allow you to download the clues for where each symbol is supposed to be located. So for example, this one says upside down exclamation point is the largest halogen. And you should know that halogens are over here. So upside down exclamation point is going to be the one as you're going in a family, as you go down, the atoms get bigger. So it'll be the one at the bottom in the halogen column. So when we go back to this guy, we're going to find our upside down exclamation point, which is not this one. I'm going to get rid of it. Oops. Back where it was. And there's our upside down exclamation point. A little trick I'll give you is you have to click on the outside edge and then use your arrow keys to move these. That'll make it a little easier. So that one belongs right there because it's the largest of the halogens. So then we're going to go back to our clues, and it says cent sign is the best conductor of electricity in period 3. Well, cent sign is located here. You have to click the edge, not the inside. And period 3, well, here's period 1, here's period 2, here's period 3, because they go across. And the best conductor of electricity is the most metallic element, and metallic elements are more to the left. So if it's the most metallic, best conductor, it's going to go there. So I've given you the first 2 already. There are 36 that you need to do. Once you get them done, I haven't made it yet, but down here there's going to be a button that says click here to check your work. And it's going to ask you a couple of questions, including who you are, who you worked with, because you do have the option to work with a partner on a Zoom on this one. Who you are, who you worked with, and some specific questions about the locations of different tiles that you moved into your periodic table. So if you have questions, please see me in the Zoom. I'll be in there the whole period, and hopefully you'll find this to be a little bit challenging, but a little bit fun, and good review for your test, which you're going to take on Tuesday. If you have any questions, you know where to find me.